retired elementary particle physicist and author of 11 books, including the 2007 New York Times bestseller, God, the Failed Hypothesis, How Science Shows That God Does Not Exist. His other books include God and the Folly of Faith, The Fundamental Incompatibility of Science and Religion, The Fallacy of Fine-Tuning, Why the Universe is Not Designed for Us, The New Atheism, Taking a Stand for Science and Reason, The Comprehensible Cosmos, Where Do the Laws of Physics Come From, and Quantum Gods, Creation, Chaos, and Search for Cosmic Consciousness. His topic today is the atheistic atom, and the name of his newest book, which we have on sale out in the lobby, is God and the Atom. Please welcome the very renowned particle physicist, Dr. Victor Stenger.
Thanks, Bill. I should mention, just to establish some credibility, is that Bill just mentioned my writing career. That started just a few years ago. I spent 37 years at the University of Hawaii as a physics professor, and I worked on elementary particle physics and particle astrophysics. I was involved in any number of experiments that led to some of the conclusions that I'll be talking about today. So my talk is based on my own personal experience. I was involved in the last experiment that I worked on, for example, was the experiment that showed that the neutrino has mass. So from the beginning, I have been deeply involved in just the subject I'm talking about. So that's I feel it was important to mention that. Anyway, like most of the other authors or speakers, I'll be talking about my latest book that just came out in April, 12th book actually, and it's called God and the Atom, From Democritus to the Higgs Boson. Now what I hope to show is that since antiquity, physicists have imagined a universe with no wood sprites, no spirits, no gods who created the universe anyway, or who play any role in human life. Let me list the model of reality that was advocated by these ancient atomists, and I'll tell you who they are in a moment. First of all, everything is just atoms and the void. The universe is infinite and eternal. The universe is accidental, undesigned, and God's played no role in the universe or human life. This was said 2,500 years ago. And it's just a view, I'll try to show, of modern physics and cosmology. In fact, there's even a hint of evolution by natural selection in some of the writings of the ancient atomists. The view of the world as matter and nothing else was first proposed in ancient Greece by Leucippus and Democritus. They lived in the 5th century before the Common Era. Atomism became part of the philosophy of Epicurus, who lived a generation after Aristotle. Epicurus developed a unique world system based on atomism that repudiated most of the teachings of Aristotle, Plato, and the other philosophical schools of his time and place. Epicurus' teachings were immortalized by the Latin poet Lucretius in an epic work, De Rerum Natura, The Nature of Things, that was written in Latin hexameter at about the time of Julius Caesar. So this is still before the Common Era. Let me list some of the basic tenets of Epicureanism. First, our earthly life is all there is. The punishing and vengeful gods of myth do not exist. What gods do exist have no concern for humans because they live outside of the world, at least out of our world, in a state of perfect happiness. If they're already perfectly happy, why should they have to deal with imperfect humans? And humans decide proper conduct by reasoning about the best actions to pursue. And justice is defined as dealing with others for mutual advantage and can change as circumstances change. However, atomism was far from a popular view in the ancient world. Here are some of the people who strongly opposed atomism, primarily because of its atheism. Plato, Aristotle, the Sophists, Cicero, the Platonists, and of course, Christians. And when in the 4th century, the Catholic Church took over the Roman Empire, it suppressed all forms of thinking except its own. Prior to that time, during the age of what they call paganism, but at the age of when there were multiple gods, things were much more easygoing. But once they took over, you had no choice but to be Christian, at least if you lived in the nations they controlled. Well, anyway, atomism was certainly near the top of the list of the heresies that had to be stamped out. Now, Lucretius' poem, the Rerum Natura, remained lost for over 1,000 years during those dark ages when the Catholic Church ruled Europe. Somehow a copy survived in a monastery in Germany, and it was rediscovered in 1417. And here's the first page of a copy that was made from that original that's in the Laurentian Library in Florence. And I was able to view the complete manuscript there when I visited Florence and the library last year. It's a very famous library that was designed by Michelangelo. Now, thanks to the survival of the Rerum Natura, atomism was revived during the Renaissance, and it helped trigger the scientific revolution that followed. Indeed, Newtonian physics is based on particle mechanics. It's based on atomism. For example, you take this equation, the famous equation for the parabolic motion of the projectile that you derive in freshman physics from Newtonian mechanics and from the law of gravity. And notice that the projectile is treated as a particle. All of Newtonian physics is particle physics. And when it's applied to things like solids and liquids and gases, it's still treated, these are treated as particles, as we'll see. Now, early in the 19th century, the chemist John Dalton proposed an atomic theory to explain the properties of chemical reactions. Now, although they accepted the theory, most chemists refused to believe that Dalton's atoms were in fact elementary particles, since they saw no evidence for any particulate nature of matter, at least in the work that they did in their chemistry laboratories. However, physicists did find such evidence. They showed that heat phenomena, for example, could be nicely explained as the statistical behavior of the motions of many particles inside a body. For example, they were able to calculate the behavior of gases and fluids from particle mechanics. All the laws of thermodynamics that had been previously inferred from macroscopic observations of things like steam engines and so on were derivable and were derived by people like Boltzmann, Maxwell, from purely particle mechanics. And this is a well-known equation, the ideal gas equation, that was, you could It's derived in freshman physics courses, just assuming the previous picture that's now disappeared, of atoms inside a container bouncing around like billiard balls. Now, the final proof of the existence of atoms occurred early in the 20th century with measurements of what's called Brownian motion. There's an animation here, and you see that yellow blob is something like a pollen particle or even a dust mote in a sunbeam, and it's hit by all those black dots, which are the invisible atoms, which you don't actually see. And what Einstein did, not many people realize that, but in 1905, when Einstein wrote his famous papers on relativity, special relativity, and also on the photon theory, photoelectric effect, he wrote a paper on Brownian motion. And he showed how you could calculate the scale of atoms by just the jaggedness of the paths of those particles, of that pollen particle, the Brownian particle. And that's because you can imagine those black dots being more numerous and smaller, then the motion of that blob would be smoother. And if you imagine them being bigger and less frequent, the hits being less frequent, you can imagine it being more jagged. So Einstein just derived an equation that showed how you could calculate the scale of atoms just from measuring that jaggedness. And shortly after, French physicist Jacques Marat carried out the measurement and determined that a gram of hydrogen contains almost a trillion atoms, 6 times 10 to the 23 atoms in a gram of hydrogen. And that's what we call Avogadro's number. So Einstein was able to show how to measure Avogadro's number, and Marat was able to do that. And that set the scale of atoms. For example, if there's 6 times 10 to the 23 atoms per gram, then there's 1 over that. 1.6 times 10 to the minus 24 grams in an atom of hydrogen. So you can measure the size and the number of atoms. And this was really the first time that it wasn't until the 20th century, in other words, that there was real evidence that for the atomic nature of matter. Of course, it was verified very quickly by the nuclear physicists and atomic physicists in the early 20th century. Now, although the existence of atoms was firmly established, they were still not directly observed until much later with a device called the scanning tunneling microscope. And here's a picture from the scanning tunneling microscope of iron atoms sitting on a copper surface. So early in the 20th century, physicists using the higher energies that were available with radioactive decays, like alpha decays and so on, nuclear decays, well, we now know were nuclear decays, they didn't know it at the time, and eventually particle accelerators, were able to split the chemical atoms into more basic ingredients. And so the term atom, which originally meant uncuttable in Greek, is still referred to things like hydrogen and oxygen and so on, but we now know that they are not uncuttable, that you can't split them apart in chemical reactions because chemical reactions don't have enough energy, but you can split them apart with nuclear reactions. And that's what people began doing early in the 20th century. So here's the picture that developed. An atom is composed of a nucleus, and then there are electrons that swirl around it. Now, it's important to realize that this picture is not very accurate. The nucleus of an atom is really 10,000 times smaller than the atom as a whole. It's about as big as a fly on a football field. So if you imagine a football field is the atom, then the fly is the nucleus. That's how small it is. And furthermore, the electrons didn't orbit around but they don't orbit around in planetary-like orbits, well-defined orbits, but rather they form a rather fuzzy cloud around the nucleus. But that wasn't the end of things, and first of all, it was found very early in the 20th century that the nucleus of an atom was composed of protons and neutrons, which are generically called nucleons. And for the longest time, they were thought to be elementary particles. But then by the 1960s, when I started doing particle physics, it was found that the nucleons are composed of more elementary objects that we call quarks. Each nucleon, proton, or neutron is made up of three quarks. And this led in the 1970s to what is called the Standard Model of elementary particles and forces. It was shown that a small number of elementary particles actually constitute all of known matter. And this is the table of elementary particles in the Standard Model. The pink boxes are the quarks. The green are, well, leptons. The electron is an example of a lepton. The neutrino is a lepton. And then over there, the blue, in the blue column, are the force carriers, the particles, so-called bosons, that carry the forces. Now, actually, even though there are this many particles, and there are antiparticles as well, it sounds complicated, but really, all the familiar matter is composed of just those three circled particles. The nucleus of every atom we know is made up of U and D quarks, up and down quarks they're called, and then the electron swirls around it, and every atom in the universe is just made of those three particles. And that's everything. That's you and me, that's rocks, that's trees, that's your cat. There's no special biological ingredient of any sort that distinguishes life from non-life in the world of physics. Also, it's worth mentioning that let me just say that to mention that circle over there around the gamma, the symbol gamma is the symbol of the photon. The photon is high energy photons and gamma rays, so we use the symbol gamma to represent photons. Photons are the particles of light. Light is matter. Light is just as, don't anybody ever tell you that light is energy and electrons are matter. There's no distinction. Light is just as much matter as anything else. That's the part of my story, is that there's nothing but matter. No other ingredient in the universe that we know of. Anyway, so there you have it. Those four particles constitute everything in our experience. It's all we need to know about everything. At least everything in our experience. We'll see that things are a little bit more complicated. And of course, part of the Standard Model is this thing called the Higgs Boson. The Higgs Boson was actually predicted back in 1964, and then became part of the Standard Model, and I'll talk about that in a moment. Just make one further point about the Standard Model, and that is it's agreed with all the observations since its inception. It came out in the 1970s, 40 years, there hasn't been a single experiment done in all science that has disagreed with this model. And that's quite simple, as you see. Only four particles. For most of matter, now these other particles, there are other quarks. There are two other generations of quarks and leptons. There's three kinds of neutrinos. There's three kinds of electrons. There's an electron and then two heavier versions of the electron. Those heavier particles all exist in nature. They occur in high-energy particle accelerators. They occur in cosmic rays. But they're very unstable, and so they don't exist as a stable part of the known universe. But they're there. And they were there in the early universe as well. Okay, so let me talk about the Higgs boson. The Higgs boson is a crucial part of the Standard Model and accounts for the mass of elementary particles. And here's crudely how it does that. Higgs bosons are particles that fill the universe, at least in this theory. The universe is filled with a field of Higgs bosons. And anytime I use the term field, I'm not talking about anything continuous. Every field that we know of is made up of particles, is made up of quanta. That's what quantum field theory is all about. Anyway, the elementary particles of the table that I just had on the screen are all intrinsically massless. They all have zero mass to begin with. And here's how they gain their mass. They travel at the speed of light like any massless particle does. And as they move through this medium of Higgs bosons, you see the particle moving through the medium. Even though it's going at the speed of light, it's scattering off the Higgs bosons, and that's slowing it down, at least its progression down across the board, and so it's effectively slowing down. It's acting more sluggish, it has more inertia, and that's the quality that we associate with mass. So mass comes from this source. And that was the proposal that was made back in 1964. And people have been looking for the Higgs boson until last year, when it was finally found. And now I'm going to tell you about that story. Here's the Large Hadron Collider, which is in part of the CERN laboratory in Switzerland, Geneva, Switzerland. And you can, this aerial view shows, has superimposed on it. You can't really see these things from the sky, from the sky because they're underground. But you can see these rings, individual sets of rings of increasing diameter. And the largest ring is the one that has the highest energy. And the other rings feed it. In fact, those other rings were earlier accelerators at CERN, going back 30, 40 years, some of them. So there's a series of rings that accelerate the particles faster and faster. They're very near the speed of light when they come out. And anyway, this device, this Large Hadron Collider, cost about $10 million and involved the work of 10,000 scientists from over 100 countries. And it's by far the most sophisticated scientific instrument that was ever built, including any of the satellites and so on, or wonderful experiments in their own right. This is still the most sophisticated. Now, let me show you the two experiments that observed the Higgs. This is one of, oh no, sorry, first I want to show you, this is the tunnel inside, down underground, the 17-mile tunnel. It has this vacuum pipe that the particles travel around. There are two proton beams that travel around opposite directions, where they collide in specific places. And they're steered around a circle by superconducting magnets. All right, here's one of the experiments called Atlas. One of the two main detectors that looked for the Higgs. It involved 3,000 scientists from about 38 countries and cost about $1 billion. And if you want to get an idea of the size of it, this is actually pulled apart, but there's a man standing at the bottom there to give us an idea of scale. So that was Atlas. The other experiment is called CMS, Compact Muon Solenoid, and again, it cost about $1 billion, involved over 3,000 scientists from 41 countries. And now, these are not the only two detectors at the LHC. There are 6 other detectors in various places where the beams intersect and collide with one another. But these were the two that were designed to detect the Higgs and other new particles. Now, I want you to notice a common practice here in particle physics is that when you're looking for something extraordinary, you don't just build one experiment, you build two independent experiments. You have two different groups They talk to each other, but they also keep secrets from each other because they want to be first. There's a little competition there, and but only until you replicate an extraordinary event in science does anybody believe it. It has to be independently replicated before it becomes part of any kind of scientific study. So don't believe anything anybody tells you that's based on one experiment. It's just unreliable until it's replicated independently. Now here's a possible event reconstructed from the CMS. The orange lines are tracks of charged particles that are picked up by the detector. The dashed green lines are actually unseen paths of two photons, two high-energy photons, gamma rays, and they're reconstructed from other signals. And the bars, the orange bars and the green bars, just represent, the lengths of them represent the energies of the particles involved. So this is an example of a collision that produced lots and lots of particles, but it also produced two very high-energy photons at large angles. And then what you do in this experiment is you can take reconstruct those events. And incidentally, the data that's involved is so enormous that these 100 or so institutions around the world actually analyze a lot of the data at home. There's a combination of where they tie all these computers together to analyze these thousands and millions of events that come out every microsecond. Anyway, on July 4th of 2012, last year, both of these experiments, ATLAS and CMS, reported seeing signals at the same mass. The probability that each was the same mass, about 125, 126 GeV. GeV is a unit of energy, but we, in physics, mass and energy are the same thing. It's a billion electron volts of energy, of rest energy or mass. And so they made this report on July 4th. The probability that each individually was a statistical fluctuation was 1 in 3.5 million. The odds of either being a statistical fluctuation is 3.5 million to 1 against. That's statistical significance. If you look at ESP papers, they give you statistical significance like 20 to 1, and they expect you to believe that it's an extraordinary phenomenon. They have detected an extraordinary phenomenon. It's the difference between pseudoscience and science. The latest results, incidentally, are even more significant. But the other point that's important to make here is that there was, again, independent replications. These two groups saw the same thing with different experiments, different techniques. They still saw the same thing. And incidentally, there's been a lot of data since then, and when they first came out, they said they weren't absolutely sure this was the Higgs Boson of the standard model. Now they're sure. It fits every test that they've been able to make, that this is the Higgs Boson of the standard model. So there's little doubt about that. Here's a picture of the data. There's a bump there in this curve. The curve is, this is a plot of the number of events per energy interval, mass interval, the mass of the two photons. And you see there's a bump at about 125 billion electron volts. And that's quite statistically significant, as I said. You notice there's a background curve. You see, and the bump sits above this background. The background is very well calculated, and so the background is very well understood. And this was the result from CMS, and very believable. Now, I want to mention a downside of all this. I think it would be wonderful. I think physicists would be overjoyed that their theory has been verified. A theory that's 40 years old has been verified. But they're not too happy about it. Because none of the new particles that had been predicted to be found, even earlier than the Higgs, they expected to find some of these other particles, have not been found. They're predicted by extensions of the standard model. The standard model's fine, but we want to go beyond it. We want to learn more. And they're not there. Now, it's still not final word on that. The machine will be shut down shortly for a year, and then come back on in 2015 at twice the energy, and that should really settle the matter. But you know, string theory, which I'm sure you've all heard of, may be dead. I sure hope it is. That would please me more than anything. Because you see what's great about it is you have a mystery now. You say, why, what is beyond the standard model? Our speculations don't seem to, that we worked on for 40 years because we didn't have any data to tell us where to go. Everything fit the standard model so well, we still don't have any data telling us where to go next. So it may be that we have to go to cosmology to fund what's going on, because there are some theories that predict that there's a desert at higher energies that goes out for many orders of magnitude that we'll never be able to reach in a long time with any kind of accelerator. However, what's wonderful is that we now have these cosmological experiments, the cosmic microwave background experiments that started, there were 3 satellite experiments starting with COBE back in the 80s, and then there was WMAP, and now there's Planck, the Planck satellite that just reported its first data. And the cosmic microwave background enables you to look back to almost to the beginning of the universe. And we already have a model that fits that data beautifully. It's just a wonderful story. So cosmology may be taking over from the particle physicists. Which I kind of am happy about too, because that's one of the things I decided a long time ago, that I wanted to move into cosmology and away from particle physics. I didn't see particle physics was going anyplace. So anyway, we'll have to wait till 2015 to see what happens on that. Now, as I said, the Planck Explorer satellite may be telling us something that we can learn. And I want to say something about modern cosmology, because the ancient atomists also had a picture of the universe that's quite in tune with modern cosmology. First, the visible universe, we know, contains about 100 billion galaxies, each with 100 billion stars, and it's 13.8 billion years old. That's been well established for a long time. Oops. Let's read the second one. It contains, there are about 1 trillion planets, we figure, in the universe now, based on the observations of planets that have been going on now for several years. Now, life is probably fairly common. Primitive life, intelligent life is probably very rare, but with 1 trillion planets, the chances that there's going to be some form of intelligent life seems very likely. Now, this universe seems like a big universe, 100 billion galaxies, it's 40 billion light years in diameter, and 46. Yet, beyond our horizon is the distance which we can't see beyond, because it would have taken light longer than 13.8 billion years to reach us. But from the original Big Bang, there is this universe beyond our horizon that's much bigger than our existing universe. How much bigger? 100 orders of magnitude bigger. So our universe, that we're so impressed by its size, is like a grain of sand on the Sahara Desert. Okay? Now, that is not all. Let me hit the next button. According to modern cosmology, the universe, our universe, is just one, including all that other stuff beyond, is just one of an endless number of other universes. Incidentally, people who say, well, that's just speculation, that we can't ever detect these other universes, are wrong. It's possible for us to detect these other universes. There are all bubbles out there. Each universe is a little bubble. They may have bounced against each other, produced a little bruise in the cosmic microwave background, and in fact the Planck satellite seems to confirm something that was first seen by the previous satellite experiment, WMAP, that shows an anisotropy in the cosmic microwave background that just may be evidence for another universe. But don't expect anybody to make an announcement on that for many, many years. It's going to have it would be such an astounding result to have evidence of another universe that it's something that would have to be tested over and over again. However, the point is, it's in principle detectable. So anybody who says the multi-universe is not detectable, that's wrong. It's in principle detectable. Now let's ask, what about God? What kind of God? Imagine God, the God who would preside over this. All this vast reality. I mean, sure, it's ridiculous to take that humanity, which came along only 100,000 years ago, and will be lucky to last another 100,000 years, is a special creation of a divinity that pervades over this vast reality. Now, Jesus supposedly died on the cross to redeem humanity from the terrible sin of Adam and Eve. What did they do? They ate from the tree of knowledge. Terrible sin. So if it's the Christian God who's presiding over all this, then Jesus must be continually dying on the cross every nanosecond or so on some planet in order to redeem every form of life that evolved sufficient intelligence to eat from the tree of knowledge. And that's not all. Furthermore, modern cosmology supports the hypothesis of the ancient atomists. All of this you can find in Adam, not with the detail, of course, that we now know, but the idea, the concepts were there. That the universe is, and hereby, to that name, universe meant everything there was. Now I'm using the term universe just to refer to our universe, and I've used the term multiverse to refer to everything that is. Anyway, the multiverse is eternal, as far as we know. It always was, always will be, had no beginning, no end, which means there was no creation. And if there was no creation, there was no creator. And incidentally, time runs both ways in this multiverse. There's no specific direction in time. It's completely reversible. Finally, I'm sure that you all engage in discussions with believers about the existence of God. And after you have skillfully demolished their every argument, they inevitably fall back on what they think is the clincher. And that is, how can you get something from nothing?
Use God.
Well, here's what I recommend. Here's how I recommend you answer that. You don't give him Larry Krauss's book, who tries to tell you how you can get something from nothing. Nobody does that. His argument's completely unconvincing. Here's all you have to tell him. Since the universe always existed, it didn't have to come from anything. Simple. told you almost finished. And I am almost finished. Here's my conclusion. The ancient picture of an infinite, eternal, purely material universe composed of elementary particles and nothing else continues to be our best scientific description of reality. Thank you very much.
Dr. Stenger, I wanted to, there are a lot of sci-fi buffs here, I'm sure. If you could, would you comment from your knowledge of physics on what you think the possibilities are for an anti-gravity technology, maybe cold fusion, and maybe travel beyond the speed of light, those three?
Yeah, well, actually, there is anti-gravity. The universe is now expanding with an accelerating rate that's being pushed. I haven't talked about that. Next year when you have me back, I'll talk about that. Hint, hint. It's being pushed by this dark energy, which has a repulsive gravity effect. Einstein predicted it, actually. His cosmological constant has repulsive gravity. So we think that the universe is expanding very rapidly by anti-gravity. Now whether humans would ever be able to harness that, I don't know. I can't predict, but there's nothing in the wind that, no idea that I know of that would do that. And as far as cold fusion was always a fraud from the beginning, so forget about that. What was the other one? Speed, faster than the speed of light? Well, not that I can see. These wormholes and all that stuff. I mean, it's just speculation. But that doesn't mean that you couldn't travel to great distances in a lifetime just by getting on a ship that has constant acceleration and acceleration of gravity. You can go to, let's say there was this recent planet that was discovered. I forget exactly how far away it was, but I calculated that you could get there in about 20 years, 15 years, whatever, something like that. In your time, if you turn around and go back, the Earth is going to be 2,000 years older when you get there, but that's because of Einstein's relativity. However, it's very likely, I have to add, it's very unlikely that humans will ever be able to travel any place outside of the solar system, even deep into the solar system, because of the cosmic rays would surely kill you before you got past Jupiter. And so I don't put any hope in humanity going to the stars, none whatsoever. We may send robots, but we're not going to go.
You mentioned on one slide there that there's the multiverse.
Would you speak up?
Sorry, the multiverse. Yeah, sorry. In one of the slides there, right at the end, you had said that the known horizon of our universe and the multiverse is possibly 100 times the magnitude of what we can see at this point. Is there a possibility that there are that science may find particles or speeds, like he had said, beyond the speed of light, that we just don't know about? Because you said that because of the effects of the expansion of our universe, it's increasing in speed. So is there a chance that there may end up being an exponential increase of speed because of things we just that are out of our purview at this point scientifically?
Well, first of all, there are particles that can travel faster than the speed of light, as long as they're safe moving faster than the speed of light. But if you're going to believe relativity, which has been around for 100 years now and hasn't hasn't been violated once in any experiment, you can't go faster than the speed of light. That's the speed limit, yeah. Until there's some reason to go, either experimental reason or theoretical reason, I have to go by what the existing theories. You know, I really don't speculate. I try to make, in my writing, I try to be very clear that I'm not speculating, that I'm always using existing knowledge. I'm sticking to existing knowledge because I'm not writing to promote some new theory of mine. I'm just trying to interpret what we already have in terms of things like, in terms of philosophy and theology and so on. That's basically where I fit into. That's my little niche in the writing business. Yep.
Hi, Rob from Saskatoon. I had a list of questions I would have loved to ask, but your comment about string theory, I think, pretty much zeroed it in for me right away. And it brought me back to a book I read by Lee Smolin a few years ago, The Trouble with Physics. And he was highly critical of that theory, and perhaps rightfully so. Do you have any concerns yourself about the percentage of, like, say, research grants that gets poured into this field? And is that, like, a serious problem? Would you believe that?
Well, remember, again, I'm an experimentalist, okay? And so I don't know anywhere near the theory that Lee Smolin knows. So I stick to the data, and what is happening with the LHC is it really looks like these supersymmetric particles. Incidentally, the dark matter that I haven't talked about, we'll talk about that next year. The dark matter is supposed to be made of these supersymmetric particles that were supposed to have been seen by now at LHC, and they haven't been seen. So they have to be something else. But supersymmetry, that's the idea that physics is the same whether a particle has integral spin or half-integral spin. And it's not true from our everyday experience, or even from current accelerators, but at higher energies that might be true, the early universe that might be true. That's very much a necessary part of string theory. If supersymmetry fails, string theory fails. And so does a lot of quantum gravity and so on. But not all of Lee Smolin's ideas. He's safe on that score. One more.
Your last slide, the response to theists, I'm going to call now the VIX slap. I said I'm going to call your last slide, your answer to the theists, the VIX slap. If you're okay with that. I'm anticipating the theist's answer to your answer, your question to your answer, and that is that eventually, if our universe is eternal and has always existed, that if God has always existed, that he could exist within that, and it doesn't really satisfy, as bad a question as that may be, I don't think it's going to satisfy the theists at the end, because they can always go that one step further into God is infinite, so he could transcend an eternal universe. What would your answer be to that?
I'm not afraid. I don't understand. I didn't understand the question well enough. What's the question?
Well, the question is that the theist will just push back that eternal, you say the universe is eternal, therefore it doesn't need a beginning, it's always been, but the theist can just push that back further and say, well, God is also eternal.
I can't understand him. He mumbles too much.
Am I mumbling?
Yeah.
We'll be constantly pushed back by the theists because they'll just say, well, God is infinite. More infinite than the universe.
More infinite.
I think at least
Can you have a more infinite regress than that?
He didn't create the universe because the universe always existed. So at least a creator God can't fit into that scheme. And if they want to have a creator God, they have to have a beginning. The universe has to have a beginning for there to be a creator. And there's no reason to assume the universe had a beginning or an end.
Good.
Okay.